Hello, good day. I'm Paul GOVAERTS from the Eargroup, and I'll try to comment this presentation, which I think will give an impression of our vision on the future of cochlear implant fitting. Imagine a hospital somewhere in the future accommodating a CI center and where the local ENT department is running a practice management software to collect and manage all possible data which are specific to their discipline of ENT. So not just CI, but also other otological, audiological material, nose exams, laryngological material, endoscopical material, etc. So really a practice management software program, and where the CI audiologists would like a certain CI recipient to perform a number of tests. He would choose these tests from the menu in the practice management, drag and drop them to a basket, and so the basket would contain a number of tests. They are labeled as self-tests by the audiologist. Left ear, maybe the audiologist wants to change a number of test settings, and then he decides that this patient will run the test through the Koala link. But he can also choose an audiometer or the Otocube or speakers and amplifiers, etc. And then he clicks on this button to send to the through the cloud to the patient. Sorry. And the patient will receive a message on his cell phone saying that your audiologist would like you to perform these tests. The patient would then connect his cell phone to the processor. He would open the app, which would give him a very simple, user-friendly interface to perform the test. In this case, one test can be 4 tests like in the previous example. The patient will hear the sounds through this connection, run the test, and the test results will bubble up to the cloud and will be saved there in the cloud server. This cloud also hosts the intelligent agent Fox, who will interpret the results, compare them with targets, also interpret the map by means of which these results have been generated, and then will create a map modification, a modified map, which will improve the hearing of the patient, so optimize the hearing of the patient. And imagine that in this remote center they will have access to all details of these test results so that they can monitor what's happening with their patient. I think this would make life much easier. And rather than being a faraway dream, I think all of what I've just mentioned already exists now, except for 2 components, which is the migration of the basket over the cloud to the cell phone, but that's something we are developing at this moment, so it should be ready in a couple of months from now, and the link between the cell phone and the processor, not just for the streaming of sound, but also to read and write maps to and from the processor. And this is something Cochlear is working on, if I'm well informed. But the rest is there. This management program exists. It's called AudiQueen. It is installed in a number of private practices throughout our country, Belgium, a number of hospitals, small hospitals, but also very large hospitals, university hospitals, Antwerp, Ghent, Brussels. Also in France, in Australia, and in the near future in England. And so this does exactly what I told in the introduction. It's running all day long for managing all data in the ENT service, but you can drop the results to a basket, and then the patient can execute it. He can connect not to the cell phone but to the computer. He can run ACE. ACE exists as self-test. There is the Koala link, linking the computer to the processor. ACE has a professional layout for the professional audiologist who has all kinds of controls to give the sound in exactly the way he wants to give it, but it also has this self-test mode, which runs on a computer. It also runs on Android platform, not yet on iOS, so it's not yet compatible with Apple. The results already now go to the cloud, already now houses Fox, and Fox analyzes the map, analyzes the results, creates a new result and sends it back to the local client, which would be the custom sound application. And then, as it is at this stage, the audiologist has to, or retrieves it in custom sound and has to put it to the processor, into the processor. The results I've shown you are not just imaginary results, they are real results, and actually they are the average results as obtained in our postlingual adults. So adults with postlingually acquired deafness, measured in 2016, show the distribution of results which you see here, which is quite interesting, which means that at 65-70 dB presentation level they have on average, this median, on average 85% speech understanding with a relatively narrow distribution. These results are pretty good. They can be compared to results which have been recently published by the Melbourne group, and they on average have 70% of speech understanding, also on monosyllabic words. They focused on their first quartile, so the P25, which lies at 55%, because they use it in a plea to change the indications. So their P25 lies at 55, our P25 lies at 75% speech understanding. This compares even very well with hearing aids. I've just taken a couple of hearing aid users as they popped in recently. And this is a person with 50 dB thresholds, unaided thresholds. With hearing aids, here you see the speech scores. And I've plotted them as an overlay on the statistical graph. And you see that this person who has 50 dB unaided threshold with his hearing aids has results which are like the average results of completely deaf patients with a hearing aid. They are a bit better at high levels, they are quite a bit worse at low levels, and they are as the average results at mid-presentation levels. This is a patient with 60 dB threshold, deafness here, so he is not using a hearing aid at this side, he is using a hearing aid here. These are the speech results, here is the overlay, and you can imagine that this patient would do much better with a cochlear implant. So he'd better be deaf, because with such a score at 70%, at 70 dB, presentation level, he would never pass whatever selection criteria for cochlear implantation. So this person should suffer for quite a number of years to come before he becomes eligible for cochlear implantation. This is another person, 60 dB more or less of thresholds, unaided. This is his speech with hearing aids, and you see that you can guarantee this person that he will do better with an implant. Again, sadly, he will not receive reimbursement. This person was an accountant in a big office, and it was sufficiently important to him to have better hearing, so he decided to pay it on his own. So he got implanted, and a couple of months later, this here is the hearing, the speech understanding with his implant. The results are even better in the very young kids. So these are the statistics I just recently did in all our kids who received an implant under the age of 1, on average at 10 months of age, between 5 and 11 months of age, and who now have an age to perform adult speech audiometry, which means 6 years or older, then they can do a monosyllabic word list. On average, they were 12 years, ranging from 6 to 16 years. And so I just took the latest speech audiometry from these kids. Look at these results. 90% speech understanding, hardly any variation. You can guarantee such a result to these kids. This is the cochlear group, even a tiny little bit better, not significant, and this is the AB group. Those two implants are the ones we fit with Fox. Look at these results. These results are like the speech audiometry we would find in kids who have an otitis media with effusion. And all kids, one day, have otitis media with effusion. And this led me to write this paper in a supplement of Cochlear Implants International on new indications for cochlear implants, where I argued, has time not come to ban formal CI selection criteria? Let's go back to the vision. Try to imagine that this is achieved in 1 or 2 years from now. Most of it can be done already now. I think it comes with a number of advantages. First of all, it would make fitting much more convenient and time-saving. It is very straightforward. It is very systematic, and also the results will be therefore very predictable. So in terms of ease of life for the audiologist, but also for the CI recipient, this will be very important, but not just for them. I think also for a cochlear implant company, it is very important to have predictable results, to have robust results. Also for the healthcare purchaser. if we look at the results presented by the Melbourne group, although they are very good, they vary from 0 to 100%. So you can't go to a healthcare purchaser with such results, because they will say that you cannot guarantee with any certainty a good result. Therefore, you can only give an implant to completely deaf patients. Because if there is a patient who has aided speech understanding of, say, 50%, according to this Melbourne graph, quite a number of them will have less with an implant. If you would take our results, you can guarantee that no one, or only a very, very rare case, will ever have a result worse than, say, I don't know, 50% or 40% or whatever. The third advantage is that it would really add safety. Because I haven't addressed this issue, but Fox has a lot of additional safety measures built in. For instance, it comes with a maximum step size. Fox is not allowed to take 2 big steps at a time. An audiologist can. He can move the slider from 100 units to 200 units. An apprentice can do so by accident. Fox can never. Fox can only operate within a limited space of this entire domain of map settings, etc. It's also very research prone. All data will be saved in the cloud. They are accessible. So this will be available for analysis, for surveillance, but also you can very easily make different advices, different algorithms. For instance, suppose that there is some question whether a dynamic range, an electrical dynamic range, shouldn't be bigger for better speech and noise. Then you can easily program Fox in such a way that he will promote larger dynamic ranges, that he will ask for speech and noise to be entered. You can make such a device next to the existing advice, and then ask a number of CI centers whether they are willing to participate, and they will run not the typical advice but the study advice, and in very short time you will have your results obtained in a very systematic way and very robust results. It will also serve quality control. You can guarantee a certain quality. You can do quality surveillance. You can see whether there are some centers or some audiologists or some device features which may have systematically better or worse results than others, and then you can intervene. You can obviously use it for competitive advantages. Can put it into tenders if you are a device which is compatible with an artificial intelligent agent. That may be very beneficial in competitive perspective. So I think it comes with a lot of possibilities. Now let's have a look at the improvement over time, because I know you will be very skeptical when seeing these data, so I won't to go into some more detail. These are the results as we obtained them some 8 years ago. I show you the average phoneme score. It's an index we like to use here internally. We call it the EASY, Eargroup Speech Intelligibility Index, and actually it calculates the average of these 4 scores at soft speech 40 dB presentation level 55, 70, and this is calculated twice, so it's a weight average, and then 85 dB presentation level. So this score is always lower than the 70%, than 70 dB or the 65 dB score. But I like it because it's kind of an integration of the total speech curve. It was 57% 8 years ago. It is 77% now. We improved 20% easy in 8 years' time. If you draw a line to the medians, you see that there are 2 slopes which seem to coincide with the introduction of FOX, of target-driven computer-assisted fitting, and FOX second generation in 2014, 2015. You could argue that this is thanks to processor upgrade, so we checked for this. There are 4 cases who went from a 3G to Freedom. On average, easy went down with 3%. There were 5 cases who went from Auria to Harmony. Easy went up with 5 points. There were 14 cases who changed from Freedom to CP8 or 900, easy -1, and there were 20 cases who changed from Harmony to NIDA, easy +2. So it's obvious that this plus 20% can never be attributed to processor change. Nevertheless, it is significant, highly significant at all presentation levels. And it's progressive. This is to show again that it cannot be explained by processor changes. This is the within patient gain when changing a processor. Any changes taken into consideration here. So you see that on average there is a 0% improvement with processor change. This is the cochlear group, and this is the AB group. But it is progressive. This is the average curve of our patients in 2007, 2010, 2013, 2016. It coincides with FOX. It cannot be explained by processor upgrade. Maybe it can be explained by patient learning. I don't think so, because big part of the effect is already seen within the first year after implant. This is the average score 1 year after implant. It compares very well with the Melbourne group, and actually we have exactly the same average as they have 1 year post-op. Here I like to make a distinction between 2 groups: those who have a perfect articulation of their own language, of their own voice, and those who have a speech intelligibility rating of 2, which means that there are some minor problems in their own articulation. I think, although both are labeled in our medical files as postlingual, I think that the second group are not really confirmed as postlingual, and there is some hesitation whether a true postlingually acquired deafness can yield articulatory problems. So to stick to a very strict definition of postlingually acquired deafness, I prefer to only take patients with a label of postlingually acquired deafness plus a perfect articulation. So from now on, that's what we will see. You see that the average results are tiny little bit better than the average results of the total group. In our collection, these stand for 75% of the patients and these for 25%. This is the distribution, so slightly higher than the Melbourne group, less variation. And this also is progressive. So the result 1 year post-implantation in 2008 was far less than in 2010, 2013, 2016. So big part of this 20% improvement is already acquired within the first year. So this has to do with the switch-on procedure. It is not a long-term learning effect of the patients. So it is something within these first 12 months after implantation. But even this cannot entirely explain the effect. It doesn't stand for the full 20%. If we look at the results as measured in 2015, 2016, so of the last 2 years, we see that they are significantly better than years ago. But what is more interesting is that we see that there is still further improvement between 2015 and 2016. So if we take patients who have been using their implant for a number of years already, on average 10 years, who have been fitted last year by means of Fox, so they have received the best map from Fox 2015. They come in now, we test them, and we ask again advice from Fox 2016 now. Then we see that in dark green, this is the speech audiogram at the beginning of this session, so with their old map, with their home map. And in light green, this is the speech audiogram with the new map as it is generated within this session by the latest Fox. On average, this is an improvement of a couple of percentages, significant for all presentation levels. So this means that big part of the 20% improvement is achieved already within the first year, so it's a matter of fitting. It's not a matter of processor. And there is still a marginal increase thanks to the incremental learning of Fox. Fox has become stronger over the years. So to conclude, I think that it is very important to observe that our speech understanding has improved by 20% in 7 or 8 years' time. I think that is very, very significant. That this cannot be explained by processor upgrade. It can hardly be explained by patient learning. It can be explained to a large extent by first year effects, therefore fitting, and by incremental learning in Fox, such that even after a couple of years of CI usage, they can still gain within one session thanks to the fact that Fox this year is stronger than Fox last year. This brings us to Fox. And I will try to give you a glimpse of how Fox works. It has all to do with optimizing a certain process, the process of fitting. And this can be compared to any other process optimization. For instance, the heating of your room. This can be done in the classical way, by a fire and by wood. And in the hands of an expert, this can yield very good results. That is someone who knows the fire, he knows the wood, he feels the temperature, he knows what is comfortable, he knows the time delays, etc. And he can keep the room quite comfortable. Nevertheless, we have learned that this can be optimized. And that for this to happen, we need three components, and these components are essential in every optimization process. We need a sensor to assess the state of the system at any moment. In this example, it's a thermometer. We need an actuator, which is the engine which is capable of changing the state of the system. And we need the controller, which receives the measures from the sensor, knows the target, knows the engine, and knows how to drive the engine to bring the state of the system closer to target. This is not different for cochlear implant fitting. The sensor obviously is not a thermometer. The sensor needs to sense the state of the system. The system is the aided cochlea. So what is the state of the system? It relates to its function, which is the coding of sound. Sound has three components: intensity, spectral content, and temporal content. So the system is doing well if it conveys this information well, or vice versa. So we have to measure the quality of the coding of intensity, spectral content, temporal content. We can do this at three levels: detection, discrimination, and identification. And we must realize that detection and discrimination are the true tasks of the cochlea, competences of the cochlea, whereas identification is not. Identification of a signal is the result of quite a bit of central processing of what comes out of the cochlea. Central processing by means of central auditory pathways, by means of cognition, of linguistic knowledge, of lexicon, of memory, etc., etc. That's important if we pick our tests and interpret the test results. We have audiometry, and audiometry is a test at this level. It assesses the detection of sound and considers intensity and spectral components. Speech audiometry is way up. It is a very high level of identification, requires a lot of central skills and capacities. So over the years we have developed a number of other tests, validated them, got normative data, etc. for assessing these other fields in the matrix. And all these tests with the audiometry and the speech audiometry have been assembled in this package, which is called ACE, stands for Auditory Speech Sound Evaluation. For your information, it will be fully integrated into AudiQueen at the end of this year. So in 2-3 months from now, it will be an integral part of AudiQueen. But that's the function of ACE. We have learned that for the cochlear implant fitting, these tests are most relevant. Audiometry, speech audiometry, and then for intensity coding we like to use the loudness scaling, and for spectral coding we like to use the spectral discrimination task in ACE. We don't use a temporal test simply because we know that the current cochlear implants don't convey temporal information. So there is no use in testing it. We do use it for electroacoustic evaluation, we use it for hearing aids, etc., but not for cochlear implants. So these 4 tests together yield over 60 measured points in our patients, which is a bit more than just a thermometer. It's a bit more complex than just a thermometer. It requires resources, special equipment, expensive equipment, soundproof booths, expensive audiometers, qualified personnel, time, etc. And that's the reason why we developed Koala, because Koala creates a direct link between the computer and the processor to stream the sound to the processor. So you don't need the booth any longer, you don't need the audiometers any longer. It's all part of ACE. And it's also the reason why we have developed the self-tests. So most, if not all, tests of ACE can be performed as self-tests on a touchscreen, Windows environment or Android environment. So this will facilitate the testing tremendously. Then there is the actuator. The actuator is the engine which can change the state of the system. In our case, obviously, this is the cochlear implant, which has to convert the information from the input signal into electrical code. This is a very complex piece of equipment. In 2012, we have organized a debate in Antwerp where we invited 100 experts in this field. Sorry, there was a voting system, so I could raise a number of questions, and one of this was the following. Suppose you have an AB harmony with all parameters left to default values except for the T and the C level, which were put to 50 and 250 current units, and suppose you're giving sound for audiometry around threshold, so the minimal audible level, 20 dB say. You have set your system to give between 50 and 250 current units or clinical units. How much do you think you're giving when stimulating at threshold? How much do you intend to give? These were the answers. There was no consensus whatsoever. 57% said that they intended to give T level, something around T level. All the others believed they were giving something different. Now the most remarkable point is that this was the correct answer. So only 5% had the correct answer. We had several of these questions from all different companies, and the results were consistent. Which means that the experts hardly know what to expect from their device. And this is not a blame. It's just reality. And it only shows how difficult it is to predict the behavior of the implants. And that's why we've created what we have called a uniform graphical model to model this behavior for the 4 different implants in the 3 different domains. This is the acoustical domain, that's our domain as audiologists, dB SPL, and there is the electronic domain in dB full scale, so it's the bits and bytes in the processor, and there is the electrical domain in current level, nanocoulomb, which is what comes out of the electrodes. And so we have modeled the behavior of the implants in an interactive application where you can play with the map parameters and see their impact on the graph. Now, this remains very difficult to use because it's simply very complex, and what is shown here is the graph of one electrode, so there are 22, and one particular map, so each other map has a different graph. And that's the reason why computational power can help us out. And this is the logic. In the beginning, in the first generation of Fox, we used deterministic logic. The building block of this is what you see here: if A, then B. If certain conditions are met, then change the map like this. With such a simple building block, you can build quite complex rules, like if a certain condition exists and another condition and a third condition, or a fifth and a sixth, then if the map is like this, change the map like this, for instance. And this is what the first generation of Fox actually did. I won't go into details. And this yielded quite interesting results. For instance, we could show, with the results obtained in 14 centers, 250 patients, we could show that it was feasible with such an approach to bring the system to preset targets. This graph shows that the average patient, after automatic switch on, had almost 60% of his 60 points on target. It also shows that there was quite some variation. Some patients had much less results on target. Others had 80% of their points on target just after automatic Fox switch on. If not on target, and if Fox came into play, this increased to 80% with much less variation. And if we accepted a bit more tolerance, it was 90% of points on target with even less variation. So very robust. And this tolerance, for instance, means that if we define target at 30%, then this is the result. But if we say, okay, 35 is near to target, and we also calculate this as positive, then we have 90% success rate. But this is obviously getting to target. It doesn't mean that you have good speech understanding. So a second study was performed by different centers in Europe, in Germany, in UK, and in France. A double armed study was performed, randomized. Patients received either a typical manual fitting in green or a Fox strategy in red. The endpoint was at 6 months, and it was shown that words in quiet were significantly better with the Fox arm than with the control arm. And this was also the case in noise, sentences in noise. But still, we felt that this was not going to solve all issues for several reasons, but I like to resume them as saying that this deterministic logic will ultimately fail because life simply is not deterministic, which means that you cannot predict everything in a very precise manner. Just give you an example. If you increase the energy at a certain electrode, it would be normal if this would sound louder to a patient, and in many patients it will, but every now and then there will be a patient who will score this as softer. This is something you simply cannot predict, and this you cannot grasp with deterministic logic. And that's the reason why a couple of years ago, 5 years ago or so, we decided to have probabilistic come into place. Probabilistic is of this type. If a certain condition is met, then we don't assume with certainty that a certain outcome will be obtained. Rather, we say that if a certain condition is met and we perform a certain map change, then a certain outcome may be obtained with a certain probability. But it is also possible that we will have another outcome. So for instance, if we increase the energy, there is a high probability that the patient will find this louder, but there is a probability that he will say there is no difference, and there is a third probability that he will say it's softer. And each outcome comes with an appreciation, which is called in AI language a utility. So the utility says whether we appreciate this outcome or the third outcome. And we can multiply the utility with the probability and then sum them up, and then we get a global utility for this new map, which tells us that this new map, if we apply it to 100 patients, and knowing that in 80 patients he will yield this result and in 20 that result, etc., that for the group of 100 he will have been beneficial to the extent of this utility. Now the nice part is that we can ask the computer to make this calculation not for one map only, but for a number of maps. Just to generate a number of maps and make this calculation, and then return the map with the highest utility to us and say, okay, try out this map because I think that this will be most beneficial. And that's exactly what Fox does. So you enter a result into Fox together with the map which generated this result. Fox will then create a number of new maps, and for each new map Fox will calculate the utility. He will then return the best map plus the prediction. So for instance, if the previous map gave 60% score, Fox will say, okay, try out my new map because I predict the new point to lie here. There is a probability, say, I don't know, of 30% or 40% that your new result will lie around the current result. There is a probability of 50% that it will be slightly better, between 65 and 70. There is a probability of 30% that it will lie between 70 and 100. He will do this for every point. And then you can give this map to the patient, you can do the audiometry again, and very often you will find the results falling in the predicted range and even very often spot on. And this is exactly how Fox works. On top of that, Fox will receive or interpret this new map or this new result also. If you enter it into Fox, he will compare it with the predicted result, and he will fine-tune his algorithms, trying to make the prediction more efficient or more precise. So there is an intrinsic learning effect of FOX over time, and this results in an incremental benefit. Even after 10 years, FOX will still be capable of improving the map. This is an example of a case who entered years after implantation with this speech audiometry. It was entered into FOX. FOX suggested a new map, and this is the new map. And this is a second patient, even if the result is very good, 90+% of speech understanding. FOX appreciate this, and FOX here says that speech audiometry indeed was very good, and therefore it may not be wise to change the map. Nevertheless, he says, I have examined 24 million alternative maps, and maybe there is one which may yield even better results. So if you are ambitious, why not try it out? He also gives the utility which comes with it, and after a while you will start reading these utilities and interpreting these utilities. Now they don't mean anything to you, obviously, but for me it means that there is a small probability to have a small benefit, or there is a reasonable probability to have a small benefit. And so this is exactly what happened. The new map was given to the patient and we measured a very small benefit. And so these are other examples which show you this incremental benefit in long-term users, just thanks to the fact that FOX has learned over the last 12 months. It's not always a success. This, for instance, is a patient who came in with this map. FOX suggested an optimized map, but the result with this optimized map was the orange one. And so this is very comparable to a navigation system in your car. He will also calculate probabilistically the road which will bring you to target in the most efficient way, but every now and then you will make a mistake and you will lose time rather than win time, or you will lose your road rather than find it. This also happens with FOX, and so it requires the audiologist to be attentive all the time and to be capable of overruling FOX if need be. But this incremental game is a definite fact and an asset of FOX. So as I've shown you earlier in this presentation, we have recently run this evaluation in 20 consecutive patients who had on average 10 years of CI experience between 2 and 16 and who just came for their annual visit. So they had been what we call FOXed last year in 2015, and this has yielded the red curve, and now they came in and they were measured, and this is the red curve, and then they were FOXed, and instantaneously this resulted in the green curve. The within patient comparison showed that it was a significant improvement of a couple of percentages only, 2, 3, 4%. But imagine that this happens every year, then in 10 years time you can imagine to have 10-15% improvement. In addition, FOX is not limited, restricted to only touch the T and the C levels like most audiologists are. FOX is allowed and capable of changing the other parameters, and he does so quite a lot of times. He changes the loudness growth, he changes the TSPL and the CSPL, and this is the same for other implants.